Hi everyone, I'm Tom, and I'll talk about scaling Iceberg ingestion with Apache Beam. I worked on this with some of my teammates, Jayaj and Ahmed. Just a quick summary of what Iceberg is and why people are using it for data processing. It provides structured SQL-like table capabilities for data lakes. It is the bridge between compute engines and cloud storage. It provides metadata tracking of data, so you don't need to scan everything each time, and provides snapshots so you can make consistent reads across your data. People are starting to use Iceberg because you don't get locked into a specific type of vendor or processing engine. It has great speed due to the metadata. You can make safe and concurrent read and write operations. You can add or drop columns, and you can time travel to points in the past for your data. So what my team worked on is investigating how Apache Beam and Iceberg IO sync perform. So we started with some benchmarking to see if there's any improvements to be made here. To set up the benchmarking, we wanted to compare both a Flink job and a Beam job. So our pipeline was reading from Kafka and writing to Iceberg. The Flink job was written with the Flink table API, and the Beam job was written in Beam Java. Yeah, so with those pipelines written, we generated 1 terabyte of backlog for a Kafka topic. Each message in the topic had was 10 kilobytes, and the schema was just 2 fields. And for this testing, we used Hive Metastore for the catalog. Our benchmark showed some drastic results. The Flink job was around 10 times faster than the Beam job. It had better characteristics of the output files, writing files around 400 megabytes versus 40 megabytes on Beam. That is, the larger files is a good property for writing to Iceberg because it can reduce the amount of metadata and make your reads faster. And the Flink job had better resource utilization. The worker is using almost all the CPU possible, whereas in Beam on Dataflow, the CPU was not very consistent across VMs and for the lifetime of the job. Showing this in some graphs, the Beam and Dataflow job is on the left. Some workers are at very high CPU, some were at very low CPU, and there's a lot of spikes. Whereas on the Flink job, all the workers were mostly around 80% CPU utilization, which was nice. The Flink pipeline had some differences where it did in-memory aggregation. So there was less back and forth with data to some backend system, and then writing those files directly to Iceberg after the in-memory aggregation. In the Beam pipeline, there is some additional work done by shuffling data and writing it to state to help aggregate data to be written into Parquet files. And those were updated in the Iceberg catalog after. So with all of those differences, we wanted to look at what improvements we could make. These are a collection of various improvements we worked on. The first one being compression. Defaulting to inefficient compression was wasting a lot of CPU for the Beam job. Metadata caching, the Beam job was looking up metadata for each input it received, which was inefficient and exhausting quota if you're using some service that gives you a quota on your Metastore. Direct writes, we wanted to avoid writing some files to state and rereading it before writing to Iceberg. We realized in some cases, we can write directly to Iceberg and still have the desired large file characteristics. And finally, autosharding. When we can't write directly to Iceberg, we wanted to improve autosharding to result in those larger data files. So I'll talk a little bit more about each of those improvements we made and what the results looked like before and after. First was compression. In Beam, all the Iceberg jobs were using gzip. And since Iceberg updated the default table compression to Z standard, we realized we could check the table properties and use that compression algorithm instead of forcing it to gzip. So after this Apache Beam change went in for version 270, Beam will use the whatever compression is defined on your Iceberg table, and usually that's Z standard, which performed a lot better. Here's some load testing. The original job is on the left and the updated job is on the right. You could see the CPU improved, and the job was able to clear the backlog a lot faster than the initial run. The next improvement we worked on is metadata caching. For, like I said earlier, for each input to the Beam job, it was looking up the table metadata. And in this case, we were using Big Lake Metastore, and we quickly would exhaust the quota, and the pipeline would get stuck processing until it could get more quota. So instead of doing the inefficient lookup for each input, we started caching the table metadata and refreshing it at every 2 minutes. Next is direct writes. Like I mentioned before, in some cases, the input to the Iceberg sync may be a large bundle of items. In that case, we don't need to aggregate them to be able to write a large file. We can just directly write a large file. So on the left is showing a graph of the different transforms in the Iceberg sync, including the newly added direct write on the left branch. And the right is showing how this is fused in the Beam job. The new direct write is done in the first stage at the top, and those files that are written from the direct write are also shuffled to the final stage for committing to Iceberg, in addition to the regular files that are done with the aggregation on the right branch. Showing some results for this approach, almost all of the file size metrics looked better. There was a larger max file. The mean was more than 10 times better. In that case, the minimum was not better. But in general, there's a lot less files and the mean was much better. This also improved the cost of running the pipeline. We can see the baseline was around 20,000 cost units for a data flow job. And the experiment with direct writes lowered this to around 3,000 units. So yeah, in addition to improving the resulting output files, we made the job cheaper in this case. Next is autosharding. So in Beam, each runner can support autosharding, and in this case, we looked specifically at Dataflow's autosharding. For the Dataflow runner, the autosharding in Iceberg Sync was writing 40 files per worker. In a lot of cases, this is almost too much parallelism. It's writing so many small files. And again, that results in the slower queries. We tried manually tuning this to see if it's worth improving the autosharding. So we reduced the 40 parallel files to 6, and we saw improvements of 8 times larger files and 25% improved throughput. Because of this, we decided to look into throughput-based autosharding, which Dataflow Runner already supports. And it was used in BigQuery Sync and GCS IO Sync, so we wanted to try reusing that for Iceberg. This is using the throughput-based sharding in Iceberg Sync, and we saw improvement in the resulting files again, where the max was at the configured max of around 500 megabytes. The mean was around 200 megabytes. And that was a big improvement on the previous mean of 3 megabytes or 4 megabytes. And overall, the count of files is also much lower. Just double checking, the beam counters are approximate, so investigating specific files in Iceberg, we verified that in the experiment, most files were 100 to 500 megabytes, and in the baseline, they were around 5 to 30 megabytes. Also checking the performance, the baseline job was slowly falling behind over time. It could not quite keep up with the throughput. In this case was around 250 megabytes per second. And then in the experiment, it was keeping up with the throughput throughout. There's a backlog that shows up, but it was consistently low compared to the baseline in this case. And growth, with all of those improvements combined, Beam is able to provide a better Iceberg IO sync for customers. And on Dataflow, at least, we've seen usage of the sync grow by 20 times what it was around 6 months ago. So we're glad that this is helping grow Beam and Iceberg sync. And that's all I have. Thank you.